Throughout this lesson, we are going to look at clouds, their formation and characteristics, and how they relate to aviation. We shall also look at precipitation and how it is produced. This lesson links strongly with the principles of stability, which we discussed earlier in this course. Clouds form the basis of what we call weather, and certainly for aviators, they are significant indicators of what is happening within the atmosphere. So it is important to recognize the signs that are in the sky. But how are they formed in the first place? Cloud amount is measured in octas, or eighths of the sky. Imagine the whole sky is divided into 8. The number of eighths of coverage is given for each cloud layer. Cloud is formed by the vertical movement of air. As it rises, it cools adiabatically. If enough cooling takes place, saturation is reached, and the water vapour condenses out into cloud droplets. The most simple form, as we see here, is a cumulus cloud appearing from a parcel of air which has been forced to rise. This is called convection, and is usually a result of surface heating. There are, however, several reasons why air will rise, which leads to varying types of cloud with different characteristics. Let us look at the convection process in a bit more detail. Consider a parcel of air forced to rise by surface heating. The parcel will then be warmer than its surroundings, the ELR, and hence buoyant. The parcel of air will therefore start to rise, and since it is unsaturated, the air will cool at the dry adiabatic lapse rate of 3 degrees per 1,000 feet of ascent, or 1 degree per 100 meters. At the same time, the dew point of the parcel of air will cool at a steady rate. Where the two meet, saturation will occur. This is called the condensation level and signifies the base of the convective cloud. Let's consider how different dew points and temperatures at the surface change the cloud base. This diagram shows how this temperature and this dew point of a parcel of air will give this cloud base. If, during a summer's day, the temperature continues to rise to this point, and the dew point falls to this point, then the cloud base will gradually rise to this point. Notice how the separation between the surface temperature and dew point has grown bigger. We can see, therefore, that if the separation between surface temperature and dew point is greater, then the convective cloud base will be higher. An approximate way of calculating the cloud base in feet is to subtract the dew point temperature from the dry bulb temperature and multiply the answer by 400. This rule of thumb will give the cloud base in feet. So, if the dew point is plus 5 degrees and the dry bulb temperature is plus 12 degrees, then 12 minus 5 equals 7. Multiplying this by 400 gives a convective cloud base of 2,800 feet above ground level. Cloud base is defined as the lowest zone in which the type of obscuration perceptibly changes from that corresponding to clear air haze to that corresponding to water droplets or ice crystals. The cloud base is the height of the cloud above ground level. How do we measure cloud base height? Well, there are several ways. The most obvious one is from aircraft reports. Another way is by balloon. A balloon is released which has a known rate of ascent. The time it takes to disappear into cloud is measured, and the height of the cloud can be calculated. Currently, laser cloud-based recorders are used at most military or larger civilian aerodromes to measure cloud-based heights accurately. These fire a laser beam upwards, which interacts with the cloud it encounters. A proportion of the beam is then reflected back down to ground level, where it is picked up by the receiver. These are known more commonly as ceilometers. At night, we can simply shine a powerful beam of light directly upwards. This gives a spot on the underside of the cloud. Applying trigonometry and using an instrument called an alidade, the angle of the spot is measured and the cloud base is calculated. You may have heard the phrase cloud ceiling, as in CAV OK, ceiling and visibility OK. Cloud ceiling is defined as the height above aerodrome level of the lowest layer of cloud, of 5 octas or more. So, we have looked at convective cloud bases and ceiling. What about cloud tops? The top of the cloud is a fairly simple concept in that it represents the transition into clear again, noted by a sharp reduction in the relative humidity. On a convective day, when we have cumulus clouds, as we see here, the bases of the individual clouds are usually at a fairly constant level, whereas the tops are at a multitude of heights above ground level. Aircraft observations, radar, and also satellite images can be used to measure the cloud tops, but the more usual way is using a height temperature graph obtained from a radio sonde. On our graph, notice how the cloud stops at the point at which the SALR meets the ELR. This part of the ELR is known as an inversion, because the temperature starts to increase with height. It is at this point that our parcel of air, which was following the SALR, is no longer warmer than its surroundings, the ELR, and therefore will no longer rise. So far, we have been considering convective cloud, where a parcel of air is either buoyant or stable in the atmosphere, and so will either rise or remain stationary, depending on its temperature and humidity. But what about layered cloud, like this? Let's consider our temperature height graph again. If, on our graph, we introduce another line, called the dew point curve, to go with the ELR, or environmental lapse rate, it might look something like this. These two curves together show us how moist the air is, and are typical measurements that are taken by a weather balloon. If they are close together, the atmosphere is very humid. When the temperature of the rising air is the same as the dew point, we have saturation, and cloud will form if cooling continues. The graph can tell us this, and shows where layers of cloud could be found. Here, and here, we would expect to find layered cloud, such as stratocumulus or altostratus. Whereas here, the ELR and dew point curves are well separated, so we expect clear, unsaturated air, and hence cloudless conditions. Cloud can be produced by yet another mechanism, turbulent mixing. If, for example, we have very light winds overnight, layers of air with very different humidity properties can develop, but with no cloud. After sunrise, there may be an increase in wind, causing these layers to become well mixed. Putting it simply, when this happens, the moisture contained within the whole layer can become concentrated at the top of the mixing layer, trapped beneath an inversion. The moisture content is enough to produce saturation, and hence a layer of cloud beneath the inversion. The cloud is not turbulent itself, but created from turbulent mixing.